So, one of the primary philosophy that we had been following right from the IS 1 course, Information Security 1, 2, 3 and currently the 4, is that the theme has been secure systems engineering rather than looking at security of a particular part in isolation. What we meant by secure systems engineering is that security cannot be viewed in isolation, say at a software layer. If you say that I am making a secure software, there are a lot of assumptions that we make before we say that this is a secure software. Or if I say I am making a secure hardware, again there are a lot of assumptions that somebody who is going to write the software would write a secure software. So, security spans across all the domains. You need to have security at the hardware digital level, otherwise there could be things like side channel attacks where people can say measure, for example I have a secret key but my circuit consumes lot of power when it is processing a 0 when compared to when it is processing a 1. One need not know the secret key, you can just keep measuring the power at the underlying circuit. If it consumes lot of power, then he says okay, the key that it is processing, the bit that it is processing is 1. If it is consuming less, then it can say that the bit it is processing is 0. So, now by this, if it starts profiling the power over a period of time, then basically it can find out whether what is the key, like it can be 1 or 0, 1, 0, 1, 0. So, the entire key can be leaked without actually having access to the key, and this is called side channel analysis. I do not actually look at the key, but I study a parameter which varies because of the variations, the ones and zeros in the key, and by that I could actually go and find what the key is. So, this is a circuit level vulnerability. On top of it there is a microarchitecture, on top of it there is a operating system, then there are system programs like compiler, other development environments, and on top of it there is an application software. So, with all these 5 layers, one need to have a overall complete outlook before we go and certify a system as a secure systems, and this is one philosophy that we have been talking of. So, I will just start off with one of the slide that I put in Information Security 1 3 years before, right. So, these are the 5 layers. There is a digital hardware, there is a microprogramming, then there is operating system, then there is an assembly language level or your system programming level, and then there is a high level programming. Now, people who work at one level do not bother about the other, right. So, if I am working as at an application level, I do not know which compiler is going to compile, which operating system is going to execute. I just write a program and then assume that other things will be taken care of by the other layers. Similarly, if I am working at the operating system, I really do not know what the hardware is as long as certain interfaces are properly set. Not understanding what is happening in the other layer, being ignorant of the other layer, you start writing programs assuming that those layers will do what it is supposed to do, which may not be the case, and this ignorance is essentially where vulnerabilities creep in, where the security loopholes come up, and this is what we are told at that point of time when we discussed this in the Information Security 1 course. We did not have a case study that will span across all the 5 things. Now, the current meltdown that is reported widely in the literature now, we can basically see one attack which spans across at least 3 layers, namely the operating system, the microprogramming and the hardware layer. So, there is something that is happening to the cache, there is something that is happening to out of order execution, that is a microarchitecture, and this is because the operating system has assumed something. And so, the bottom 3 layers there is an attack, and you need to understand everything about every layer, lot of details about every layer to basically appreciate why meltdown has come up. So, this is one very important case study that every security engineer should go through, so that he is aware, he or she is aware of how things can happen, and so hence when you try to propose a secure solution, what is it that you need to have in your mind? This is a very interesting case study, and that is why we have introduced this as a part of this IS4 course. Every layer has to be a virtual machine That means that if I am working at the operating system level, I do not care what compiler is there or what microarchitecture is there, as long as certain interfaces are satisfied. If I am working at a systems programming level, like if I am writing a compiler, if I am writing a development environment, right. So I don't really bother about the other layers, I just bother about the interface I have with the other layers. So how the other layers are implemented is basically a black box, and this is very important because, as I gave an example in the information security 1 course, it's very, if suppose this type of a virtualization is not there, right, then even writing an hello world program would mean that I need to cover the entire computer science curriculum before people can start writing an hello world program. For example, you use printf, right. Now printf is, there is a device driver involved, there is an operating system involved, there is the monitor driver, the hardware part of the monitor driver is also involved, right. So we need to teach all these things before people can start using printf. Now all these things are abstracted and given as one hash include stdio.h, and then you can start using the printf, and then the compiler will borrow code from somewhere, it will borrow code from the operating system, which in turn can call some device driver which will go and print it out. So there are a lot of things that are involved in the implementation of printf, which is completely hidden, right, and that is an example of this virtualization that you are seeing in the screen. Now when we claim to be a security engineer, again I repeat, then it is not enough that I know each layer or one of these layers in isolation and say I will do something secure about that layer. That may not work, because we need to have a understanding of how that layer interacts with the other layer, and all the functionalities a particular layer wants from the other layer, how those functionalities are actually implemented. So this type of an idea if we have, then only we can make a secure system, and that is something peculiar about secure systems engineering, and that makes the whole thing much tougher also. Now let us go a little bit and say, what is this meltdown attack? Meltdown attack is nothing but any system, any operating system works in 2 modes. One is the user mode, another is the supervisor mode or the operating system mode. As a user, you know what is a process? Process is nothing but a program in execution. If I have hello world.c, hello world.c is called a source code or source program. When I compile it, I get some a.out, and that is an executable program. The moment I say a.out and press enter, then it becomes a process. So a process is nothing but a program in execution. Now every process will have 2 parts, one is the user part and another is the operating system part. Why should a process when it is in execution have 2 parts? 2 parts in the sense that the process basically exists in the memory. So the memory itself is divided into 2 parts. One part basically it will be assigned for the program, the other part is basically assigned for the operating system or the kernel. Why I need a kernel, we will just see that in the subsequent slide, but when a process is executing, it will have its own part and it will also have a kernel part. Now similarly another process is executing, it will have its own part and it will also have its kernel part. The way the operating system is built is that the user cannot access the kernel part or without proper authentication. In some sense it cannot even touch or view the kernel part, right. Now what has happened here is that because of certain issues in the microarchitecture definition and also in the circuit implementation, we can basically go, there is a way by which the user can bypass the security mechanism and go and access the kernel memory. So when the architecture is working at user mode, the processor is working in this user mode. So if you have done the information security 2 course, the processor can work at 4 privilege levels, namely privilege level 0, 1, 2 and 3. What I mean by the processor is working at the user mode, it is working at privilege level 3, which is the least powerful privilege. Okay, so it is the user mode. So it does not have lot of access into different things, it cannot execute some instructions, privileged instructions it cannot execute. So, it is just a user process, it is running there. By definition, no memory that is at privilege level 0, 1 and 2 should be could be accessed by a privilege level 3 process. Now, what this basically essentially means that if at a higher privilege level, meaning PL3, higher means numerically higher, but very less powerful privilege level, the security mechanisms that have been defined to block a privilege level 3 code from accessing a memory of privilege level 0 is breached, right. And the reason for that is some problem with the microarchitecture, right. So, the OS is built based on that assumption that the user part of the memory and the operating system part of the memory are isolated and logically isolated, and there are security mechanisms which will ensure proper access of this user space to the kernel space, but that security mechanism getting breached essentially has caused this security vulnerability. So, this is in gist what is the Meltdown attack. Now, this Meltdown attack has been discovered in August 2017 and it is published in January 2018, right. And this has caused a vulnerability in all the processors that have been manufactured since 1995, right. So, that is the impact of this Meltdown attack, and it involves almost every system like desktop, laptop, cloud servers as well as smartphones. Wherever there was an operating system and wherever there was a distinction between a user process and an operating system, the entire meltdown has an impact on that. And so, this is the major crux of this issue, and almost all manufacturers, all the major manufacturers, processor manufacturers across the globe, to name some, Intel, AMD, ARM, they have been affected by this type of a meltdown concept. To sum up, the high level idea is that the vulnerability basically has melts the security boundaries which are normally enforced by the hardware, right. So, between privilege level 3 and privilege level 0, there is a particular boundary that has been established by definition by the hardware, and that has meltdown. So, basically giving a way for a privilege level 3 process to access a privilege level 0 code. So, and this is caused because of some optimization issue. So, why did it come up? Because there in the architecture, there has been in the microarchitecture, the microarchitecture is defined well, but we try to optimize and get lot more performance, and when this type of an optimization happened, that optimization has gone wrong, and there is something wrong with that optimization which has caused this. There is something went wrong because of that optimization that has caused this particular vulnerability. So, with this very quick introduction, we will now go into some details of this meltdown attack. I just wanted to this is a last minute addition to this course, and we wanted to do this because the attack has come, and it is very important that people who are taking this, and this is something which is involving the operating system and the hardware, and so this course is the real apt place for us to basically give you the complete details of this attack. So, these are the companies that have issued advisories, and we have more than 3 dozens of companies here who have actually issued advisories based on this meltdown attack. This is just to give you the impact of this particular vulnerability that has existed in the hardware. So, in 2 sentences, if I want to summarize meltdown, actually meltdown breaks the most fundamental point that there is an isolation between user applications and the operating system. How is this isolation achieved? Operating system assumes that this isolation is there, and the entire security that is built on top of the operating system is essentially based on the availability of this isolation. And how does the hardware ensure this isolation to the operating system? If you take the Intel hardware, there are 4 privilege levels: privilege 0, 1, 2, 3. The privilege 0 is the very powerful thing, that is where the kernel executes. Privilege 3 is the least powerful thing, where the user program executes. Now, privilege level 3 code or process cannot go and touch a privilege level 0 memory. This is the basic isolation that they have done, and that is what is now broken. So, something at a higher privilege level, numerically higher privilege level, can go and access something at a lower privilege level. So, that summarizes the first statement that we have put on the slide. Meltdown breaks the most fundamental isolation between user applications and the operating system. So, what does it mean? This attack actually allows a program to access the memory and thus also the secrets of other programs and the operating system, which it is not supposed to do, which is not true in terms of the actual user development manual which the processor company has given to you. Right. It clearly states that privilege level 3 cannot go and touch anything about privilege 0, but it is now becoming possible. Right. Now, why it became possible, and what is the consequence of that being possible, we will just see in the next set of slides. Now, I want you to go and look at the IS2 course, the Information Security 2 course, where we have spent a lot of time trying to explain how task switching happens. That is, there is a process, there is a program in execution, there is something called the context of that process. What is the context of the process? I have said in the Information Security 2 course that so there are 10 processes that are lined up to execute. The operating system will execute one by one. It will give some so it will assign, say, some 5 units of time for each process. So, first 5 units it will execute process 1, then it will pull it out, then execute process 2, pull it out, execute process 3, pull it out, and go on. So, this is called a round robin scheduling. So, every process will have a field that it is executing, and that is how every process goes to completion. Right. So, this is the basic scheduling algorithm of the operating system. Now, when I said process 1 is executing, then it is pulled out. What do you mean by pulling out? I need to save the context of that process, so that I have to restart it again, and when I pull out a process and restart it, it should start exactly at the point where it left. Right. So, that is very, very important. So, the round robin algorithm works because lot of things work because there is something called a context, and that context need to be saved at different times. Right. Round robin algorithm scheduling is one instance where the context need to be saved. One process is executing, I want to pull out that process, then put a new process in, then at some point of time the same process which I pulled out has to start executing again. For that I need to start from the point exactly where I left. So, for me to start at the point where I exactly left, I need to save the context of the process. So, context of the process is the minimum information that is necessary for me to restart the process exactly at the point where it left, and that minimum information is basically stored in what we call as the task state segment, TSS. Now, look, so what we see here on the slide is there are 2 task state segments, there are 2 processes that are executing, P1 is executing and P2 is executing. Let us say they are going to execute one after another. So, P1 executes first and it will execute for some 5 units of time, then the operating system will pull it out. When it pulls out, all its context, meaning the general purpose registers, its stack registers, its different stack pointers, all these things get stored in the task state segment, and the another process, say P2, its context get loaded. So, it will start executing. When P2 is pulled out, then all its current values of the general purpose register, etc., as you are seeing on the screen, will be saved in this in the P2 task state segment, and then the P1 will be restarted. What do you mean by restarting P1? The content of all these general purpose registers, stack, etc., will be reloaded into the different registers, and then P1 will restart. Right. So, this is how say a thing like round robin scheduling works. More importantly, when you look at the task state segment, there is one entry called CR3. So, if you had looked at Information Security 2 course, CR3 is where the page directory resides, right. So, paging resides. So, that means every process will be assigned a page table of its own. We have described that in the information security 2 course. I am again repeating that. So, every page every process will have its own page table. What will be stored in that page table? The page table will have, for the different pages that are going to be allocated to this process, the corresponding entry in the RAM. The page table is basically a translation from a virtual address to a physical address. So, I will have P1's page table, I will have P2's page table. What could happen is, inside a page table there will be some pages that are assigned for the process, there will be some pages that are actually assigned for the operating system. Why do we need some assignment for the operating system? We will now see shortly. But what happens is, what every operating system today does is that there are some pages assigned for the process and some pages for the operating system. Similarly, in P2 there will be some for the process and some for the operating system. Some pages of the operating system are shared between these two processes, right. So, this page table will point, there will be some entry which will point to some location in the RAM, and in the page table for P2 also the same thing will be pointed. So, though I am changing the page table, I can reuse the pages or I can share the pages between these two processes. And which are the pages I will share? I will never share the user pages or the memory allocated to for the process, but I will share the memory that is allocated for the operating system for lot of reasons. Okay. And so, this is one very interesting stuff, right. So, we need to understand that there are pages, specifically operating system pages, that are being shared between two processes. Let us first understand, how does a process basically talk to the OS? Why should the process at all talk to the OS? Let me give you very simple examples. Already I talked about printf, where I need to talk to the monitor, and I as an user will only give printf. I do not know whether it is some X company's monitor or Y company's monitor. I do not know how many pixels, I do not know what resolution are there, nothing I know. I will just say printf, or I will just give a graphics image. I will just open up a window where I am opening up lot of graphics image. I as a user or a programmer, high level programmer, will not understand anything about the hardware or architecture or anything of the monitor itself, or the device driver for the monitor. So, the monitor will have some controller, monitor will have some device driver. I do not know anything about anybody. Okay. So, I just write printf. Okay. So, printf, basically when you do a printf, as a process when I do a printf, I need to call the operating system routine, and the operating system routine will take the details of what needs to be printed, then it will go and contact the corresponding device driver, which in turn will contact the corresponding device controller, and then it will go and print. So, there is lot of action that happens after I just put the printf. As far as I am concerned, I do not know anything about printf, everything is taken care by the operating systems. Okay. So, when I execute a printf, I need the operating system to do lot more work for me. So, as a user process, I also need access to the operating system. That is why when a page table is allocated for me, there will be some memory allocated for me as a process, but there will be substantially at least equal or larger memory that will be allocated for the operating system to do the work that I am assigning to that operating system, right. So, I as a process assigning. One very important example which is also of very good relevance here is about malloc, right. As a C code I am asking for some memory, right. So, whom will I ask? I should ask the kernel. The kernel has to come and give me that memory, right. So, that is very important, and that is what is the interaction between the process and the operating system. Typically you can also see even lot of things like I type something on the keyboard, the keyboard has to go through the operating system to the user process. So, So, any interrupt, any type of interrupt or any system call that I make from my program or any external interrupt that comes, like I am asking scanf and somebody has to the user actually types some input through the keyboard or mouse, etc. All these things basically need OS support, and that is one of the precise reason why that the page table that we have has both the page table that we have for every process will have some pages for the process and some page for the kernel. So, a process should always interact with OS even for its execution. It is not that the process will never interact with the OS, it has to interact with the OS for many of these things. When we want to understand Meltdown with this background, we have to answer 3 questions. The first question is, we need to understand the address space. We have talked something about the address space, physical address space, virtual address space, etc. Now, when a process is requesting for memory, how address is allocated to a process for its execution? We need to understand some amount of this. And then the next thing is how one process is protected from another, and is it foolproof? What do you mean by protecting one process from another? The process is not a human being where I am having. So, the process, who represents the process? The memory represents the process. So, there is a process executing. What is the identity? What is the trace? The context of the process and the memory that the process accesses. These are the proof that the process exists, right. So, if I want to protect one process from another process, basically that means I should protect this process, X process, from accessing any of Y's memory, and I should stop the Y's process, restrict the Y's process from accessing any of X's memory, right. So, X and Y are 2 processes and I protect them means I have to protect the memory regions that both of them access, right. So, this is something. So, we have to understand the OS issue here. Then comes the hardware issue where we are trying to do something called out of order execution, and this also we have sort of covered in IS2 course to a reasonable level. So, when I have a program, it is now a C program, it is compiled into assembly, there is an order in which it needs to execute, that is called in order execution. So, the assembly language program will have X, then next instruction, next instruction. Now, by doing this, what will happen? One instruction after another instruction are going to execute one after another. But suppose I have a bunch of instructions which are not dependent on each other, and if I have enough functional units, say I have 10 functional units, 10 addition units, and I have say 100 additions to be performed, nothing is depending upon another, then basically I can take this 100 and split it across these different units, 10 for each for this unit, and then parallelly execute, concurrently execute this. When I concurrently execute, what will happen? So, I have two instructions I1, I2 following I1 in the in order definition. Now, I start executing I1, I also start executing I2. I1 can be a slow instruction, I2 can be a fast instruction, I2 can be a byte addition, I1 can be a floating point division. If that happens, I2 actually finishes before I1, then that slot can be taken by I3, and if I3 is a very simple instruction, I3 also can finish before I1, right, or after I2 I1 can finish, then I3 can finish. So, all these possible combinations are there. Now, if I2 actually finishes before I1, then this is basically called out of order execution. I am not executing exactly in the order it is given in the program, but I can actually depending upon the availability of the different units, I can go and schedule different instructions and execute them at different point of time. So, I2 actually finishes before I1, so that is what we say it is an out of order execution. Now, out of order execution is done for me to improve the cycles per instruction. Basically, the out of order execution is basically done to improve performance, timing performance. So, this optimization essentially has caused the vulnerability. If this optimization did not exist, probably this vulnerability may not have existed. So, there is a hardware. So, what we need to understand what is out of order execution. Of course, we will give you a couple of slides to basically rewind that. We have done it in the IS2 course about out of order execution also. Then the third step is of course the microarchitecture, wherein we are still working on the cache issues. So one of the important thing is the cache attack or cache memory attack. What is a cache memory attack? It is a timing side channel attack on the cache which allows the attacker to read a memory address that he is not supposed to, right. So that is also, this is basically a microarchitecture issue. So when we look at Meltdown, there are three major steps. One is the operating system, another is the out of order execution, and another is the microarchitecture. In the next session, we will talk about address space basics, basically the lot of content that I had covered in Information Security 2 and Information Security 3 course. We will try and complete some part of it, some relevant part of it from the context of Meltdown. We will do it in this session, namely address space basics. Thank you.